let's have a look at this concept of gravitational potential energy when we put an object into a gravitational field. So any mass that's placed in a gravitational field will experience potential energy. So if we place our test mass m inside a gravitational field, because it's got a mass and because it's a distance from the surface of the other object, it will obviously accelerate down. So if we want to move this object further out, we must do work on it. In other words, we need to put energy into that, and the further out we go, the more potential energy this object will lose as it travels to the surface of the other object. Now there are two cases that we can look at. First of all, if we're talking about Earth's gravitational field, we're talking about an object that's in close proximity to the surface of the Earth. So once again, we're going to do work to move this object away from the field. So away from the surface of the Earth, we must do work to that object, or the corollary of that is that we add potential energy to it, and that energy will be released as the object falls back to the Earth. So the opposite scenario here is it loses potential energy, but that energy has to go somewhere, and it's converted to kinetic energy or movement energy. So let's look at the formulae that are involved here. First of all, we do work to move this object, we lift this object. So we've got work done is equal to gravitational potential energy, or that's often shortened to E subscript P, and that's equal to the force on that object times the distance that object moves, or in other words, the whole thing is equal to the mass times the acceleration due to gravity times the change in height. Now, coming back down the other way, our loss in potential energy or loss in gravitational potential energy will be our gain in kinetic energy. So this time we've got our mg delta h is going to be equal to a half mv squared. So one thing to note here is that the higher our object is, or the further away from our larger object like the planet Earth, the more potential energy it has, and the more potential energy will be converted to kinetic energy and therefore velocity. So if we do this experiment, or do an experiment in a vacuum, our object will continue to increase its velocity for the time that it experiences that acceleration due to gravity. And the longer that happens, the higher the velocity we'll get as a final velocity as it impacts into the Earth. Now our second scenario is where our object isn't in close proximity to the Earth. In other words, the acceleration due to gravity, or the field strength of that gravitational field, is much less than 9.81 meters per second squared. But once again, we're looking at work done is equal to gravitational potential energy, which is also equal to force by distance. So let's take a scenario. We have our planet Earth with our radius of our planet Earth of about 6,378 kilometers, or 6.378 by 10 to the 6th meters. We have a mass for this Earth of around 6 by 10 to the 24th kilograms, and we have an object that's about 50,000 kilometers from the Earth and weighs approximately 100 kilograms. So we want to calculate the potential energy on that object. So we look at our formulae. We've got our work done is equal to force times distance. Substitute in our force of gravity times the distance that it moves, and obviously our force of gravity is going to be equal to g m1 m2 over d squared. So we can rearrange everything here. So our potential energy, or EP, is going to equal, and we've taken 1d from this side and 1d from this side, so our potential energy is going to equal g m1 m2 over d. And from our series of values on the left, we can put those into our equation, and we find that we come out with a value of 3.5 by 10 to the 8 joules. Now I've put a negative sign in there. By convention, our potential energy is defined as negative, and we do that because we always define in the positive direction the amount of work that we put into an object. So the movement away from the highest field strength because that's a positive direction, in other words, we're moving out further and further, so we're putting energy in the form of work, that means that an object in falling will have the reverse direction, and therefore the value will be negative. So our potential energy for gravitational potential energy is always defined as a negative value.